X-ray absorption fine structure depends on the local atomic coordination around the absorbing atom and also on electron scattering factors. In order to use extended XAFS to extract local structure information, we'll model the XAFS data with the XAFS equation that depends on both local structure and electron scattering factors. Hi, I'm Matt Newville, a beamline scientist with the Center for Advanced Radiation Sources at the University of Chicago, where I run an X-ray microprobe beamline for X-ray absorption and fluorescence spectroscopies and imaging. In this video, I'll explain the XAFS equation in some detail in order to give some insight into the nature of XAFS and what this means for how we can model experimental XAFS data. This presentation is part of the video series on the fundamentals of X-ray absorption fine structure and part of the virtual XAFS summer school at the Illinois Institute of Technology and Advanced Photon Source at Argonne National Lab. The emphasis on this video will be on the theory of extended XAFS, and there will be some math involved. Any of the quantum mechanics here will be pretty descriptive and pretty hand-wavy too. While some familiarity with quantum chemistry or atomic physics would be helpful, I don't think it's completely necessary to understand XAFS theory well enough to model XAFS data. But even if you're interested only in using XANES for chemical speciation, the simple theoretical description here might be useful too. That said, this lecture is sort of the hard one in this series and the one with the most math. So if you need to go slow or rewind it a few times, that's fine. And if you have any questions or suggestions for how to make this better or simpler, please leave them in the comment section below. Okay, in an earlier video, I described X-ray absorption as in some detail, and I've mentioned some of these properties, but let me just go over this to start with. The X-ray absorption spectroscopy goes by several names: XAS, XAFS, XAFS with an E or extended XAFS, and XANES or XANES. X-ray absorption spectroscopy is the modulation of the X-ray absorption coefficient at energies just at and above the X-ray absorption edge of an atom. We have all these different terms and acronyms, and they have some overlap in meaning, but generally XAFS or XAS is used to describe the full spectra. And XANES is really only the near edge, say within the first 100 volts or so. And extended XAFS really means the oscillations that extend far above the edge. These contain information and slightly different emphasis on information about the chemical state emphasized in the XANES portion of the spectrum or the local atomic environment, which is emphasized in the extended XAFS. The main features for using XAFS is that it's a local atomic probe. It's sensitive to valence or oxidation state, and it can be applied to basically any element with a Z greater than 2 or 3 or 4. It can work at extremely low concentrations with minimal sample requirements, especially that it does not need a crystal structure or a special isotope to work. It works on every atom. So here's an example 1s or K level absorption edge for iron. This is iron in iron oxide. And the XANES, sort of the first 100 volts of the edge, has this sharp resonance here right at the edge, and then these extended oscillations. And the emphasis here will be on, in this video, this lecture will be on the extended XAFS. That said, the XANES is highly useful in getting the local coordination environment and formal oxidation state. So here's examples for chromium, arsenic, and then iron also, where you can see that the variation of the XANES spectra with oxidation state is profound and unambiguous. So, and this, as described a little bit in previous lectures, this is dependent on what unoccupied electronic states are available for the photoelectron to go into. I'll mention this again a little later on, but most of the emphasis here will be on extended XAFS. Far above the edge, the oscillations in mu are sensitive to the distances and types and of the neighboring atoms. we'll define what we call the XAFS, the extended XAFS chi, as the oscillations that are in mu. So we'll say that mu is some smooth atomic-like factor, mu 0, or the background, at times 1 plus chi. Rearranging that says chi is the differential absorption divided by some edge step. So we'll see in our same spectra, we can model a bare atom mu of E, a background, and isolate the oscillations. We'll describe how this is done in a later video, including dividing by this edge jump or edge step. But with that, we get the extended oscillations. It's hard to see here that they continue so far above the edge. But if we convert that energy to a wave number for an electron, as we'll see shortly, XAFS is an interference effect using the wave nature of the photoelectron that is emitted from the photoelectric effect. That is, the 1s level is destroyed. Any excess energy, any energy above that edge, is converted into a photoelectron, and that photoelectron scatters. So we'll be using the electron scattering after the X-ray has been destroyed. So XAFS, it will see, is an interference effect of the wave nature of that photoelectron. So we'll use the photoelectron wave number, which is the square root of the energy with the mass of an electron and Planck's constant. K is the square root of energy. So if we take that same data and put it on a k-axis and multiply it by k squared to weight the further out oscillations, we'll see that there are oscillations that continue out to 500 volts above the edge, or a k value of 12 inverse angstroms. So that's k squared for the same data set. And since they oscillate, since there's an oscillatory function, we'll take a Fourier transform and that convert from k, or wave number, into distance r. And when we do that, we get a function here, chi of r, well, that's the magnitude of chi of r, as we'll describe in later videos, that looks a lot like a pair distribution function. It's not quite a pair distribution function, but indeed this bump here is due to the iron-oxygen scattering in iron oxide, and this is due to the iron-iron scattering from iron oxide. So it's similar to a pair distribution function. It's not exactly, and we'll get to that in later videos, but it all depends on details of the extended XAFS equation that we'll go into detail here. So to model XAFS, we have an XAFS equation. It's a little bit complicated. Comparing it to, say, Bragg's law, it's a little more complicated, but it's not terribly complicated. It is possible to use this to model data. Here, the XAFS, chi of k, is a sum over with some terms that includes n, r, and sigma squared in a few different places that are the coordination number and the distance to the neighboring atoms and the disorder in the neighboring atom. And in addition, there are these terms f, delta, and lambda that are photoelectron scattering properties of the neighboring atom. And if we know those scattering properties, then we can extract our distance coordination number and mean square disorder of the neighboring atoms. That's how we will do the analysis. We'll get these properties and use those in this equation to extract those values. It's a bit complex, but it's also pretty robust, and lots of work has gone into making sure that those techniques are reliable and robust. So in addition, as we'll see shortly, these F and delta properties, these scattering factors and phase shifts, depend on the atomic number Z of the scattering atom. And so we also have some sensitivity or specificity to the neighboring atom type. Okay, so let's go through the development of the XAFS equation in a little bit of detail, and we'll start slow with our picture of what is X-ray absorption, and we'll slowly develop this. I think it's important for understanding the nature of how this technique phenomena happens for understanding how to model the data. So this is a slightly different view of an X-ray absorption, but it's similar that it actually comes in. There's a very tight atomic core level. Let's call it the 1s level in an atom. And the X-ray gets absorbed. The 1s electron gets destroyed, or a hole is created, and that electron is ejected from the atom. And any excess energy that X-ray has is converted into a photoelectron. That photoelectron, we will consider it as a wave and has a wavelength that's 1 over the square root of energy. So here, if we plot now here horizontal and mu, our mu, and on the vertical axis the energy, if the X-ray has an energy below this threshold, this binding the 1s binding level, the absorption is low. There may be absorption due to the higher levels in the atom, but not from that. But there's not enough energy to promote that 1s level out of the core. But when we hit that threshold, that binding energy, there's a sharp jump in absorption, because now we can kick out this this electron. That X-ray has more of a chance to be, more probability of being absorbed. And then above the edge, there's this when we have more energy, this excess energy goes to this photoelectron. So X-ray absorption needs an available state for the photoelectron to go into. If there's not an available state, there's no absorption. That's basically the Pauli exclusion principle for in quantum physics or quantum chemistry. The X-ray gets absorbed, the 1s core level gets destroyed, and an electron that's of p type gets created. And so there needs to be an empty p state for that photoelectron to go into. And if there's not an empty p state, it won't be promoted out of the core. That actually goes to explain quite a bit of XANES as you adjust the Fermi level, or the continuum level for that atom. You can change, by changing its oxidation state, you can change where the energy of that threshold. But once the energy is large enough to promote a core level into the continuum, there's this sharp jump, and the sharp jump at the core level binding is a smooth function of energy above this absorption edge. Okay, so that's for a free atom or a gas. If we add a neighboring atom, we just put a scattering atom or a neighboring atom close by, well, say, a few angstroms away, as most atoms are, then that scattering atom can scatter the photoelectron. The ejected photoelectron will scatter. There's a lot of electron density in the core of that neighboring atom, and the electrons can scatter off of those electrons. And this will cause the oscillations in mu of E. As the electron scatters back, some of the X-rays, some of the photoelectrons go out from the absorbing atom. Some of them scatter back to the absorbing atom. And that scattering back, or back scattering to the absorbing atom, is what causes the XAFS. The photoelectron scattered back will interfere with itself. So this blue curve, the scattered portion, will interfere with the outgoing, here in red, portion of the photoelectron. And that scattered photoelectron partially fills that p state that we're going into. And that's what causes the XAFS. So the XAFS oscillations are due to the interference of the outgoing photoelectron with the photoelectron scattering from its neighboring atoms. It's really the density of it's really the amplitude or density of the scattered portion of the photoelectron at the core level that gives the XAFS, as we'll see. Going back to our definition of mu is some mu 0 plus 1 times 1 plus chi of k, you can see here in this that if we had this mu that was here in red and then we had these oscillations, those oscillations are chi of e, as I've shown them. And we can work out a form for the XAFS equation for chi of k that we'll use. We use Fermi's golden rule, which is how you describe any transition from one state to another in quantum mechanics or quantum chemistry. And here the two states are the atom at rest, unexcited atom, and the other state, and a photon, and the other state is the no photon and the excited atom with the core level removed. So we start with, that's the transition. So we'll say mu is, we can model as the amplitude squared of an initial state and a final state with some Hamiltonian. Here, the initial state is, again, is the core level in the ground state and a photon. And this is, of course, is not altered by the neighboring atom at all. That's just the atom at rest. Or at least not, to first order, it's not. For core levels, it's not altered by the neighboring atom. If we were looking at very high electron levels, that might be, chemistry might be included. The Hamiltonian here, the interaction, we'll just say that in the dipole limit, or for core levels that are very close to the center of the atom, we can say that e to the IKR is just, well, r is 0, so e to the IKR is just 1. We'll just ignore all that. We'll just say that that's all 1. And then there's a final state that is has a photoelectron and a hole in the core, but no X-ray at all. And this is altered by the neighboring atom because the photoelectron scatters. So the photoelectron scattering from the neighboring atom is the final state, and that all describes what the modulation of the XAFS due to the neighboring atoms. So if we write that final state as a ground state or an unperturbed final state plus the change in the final state due to the neighboring atoms, we'll say this, the delta F gives the change in the photoelectron final state that's due to the backscattering of the neighboring atom. We can expand this, and again, this is kind of hand wavy or like sort of first approximation, but you can see that we can make that into a term that's basically like the ground state final state, the ground final state, just the normal part, and then this part that's the overlap of the initial state with the change in the photoelectron final state. And this is essentially chi. There's complex conjugates, and we're going to do some hand waving, and we'll just sort of hand wave through that. So mu0 really we can say is the atomic background, and that's just the initial state overlapped with the unperturbed final state. That is the atom without the presence of the neighboring atoms. So that's going to be pretty smooth. It's going to look a lot like the gas phase, but it's going to be pretty smooth. And then there's a chi-V term that is the overlap of the initial state, the 1s level, and the final state, the outgoing, this scattered portion of the photoelectron. And that's what gives the XAFS oscillations, our chi-V. So the initial state, the core level electron, is highly localized at the center of the absorbing atom. It's really nearly a delta function. It's very tightly bound. In fact, that's sort of why we do core levels and not XAFS on the highest levels. It's pretty washed out when you try to do it at extremely high energies or extremely low binding energies. So the XAFS then in chi-K is the overlap, and I'm going to just change from like this bracket notation, again this is all hand waving quantum mechanics, into an integral. So that would just be a delta function times the scattered portion of our photoelectron. And the delta function just selects where r at r equals 0, and so the XAFS amplitude is, the XAFS is really just the amplitude of the scattered portion of the photoelectron wave function that was scattered by the neighboring atoms when it gets all the way back to the origin, all the way back to the absorbing atom. So if photoelectron goes out, part of it scatters, and the amplitude of that scattered portion of the photoelectron, it modulates and as it oscillates, its amplitude goes up and down, and that's what causes the XAFS oscillation. And that's just exactly because that scattered photoelectron overlaps with the 1s, and it puts a little bit of p electron character right at the absorbing atom, and so it changes the density of states for p electrons that photoelectron can go into. So that modulates the XAFS. So with chi being the amplitude of the scattered portion of the photoelectron at the absorbing atom, we can start with like a simple model for this. Okay, so let's just say that our outgoing photoelectron is a spherical wave. So that's the second simplest thing you can do in quantum mechanics, which is about as far as I can handle. So we can model chi-K as the photoelectron going out. So first of all, so what is this? how big is that scattered photoelectron going to be at 0? So first of all, a photoelectron goes out e to the ikr. Now capital R is the distance to our neighboring atom, not just the variable r, but that's the distance to the neighboring atom, r, capital R, and then it scatters. And I've put in some terms here, and I've played with the math so that the math will come out the way we normally describe it. But the scattering of the neighboring atom has both an amplitude and a phase shift. So this is going to be complex in the sense of having real and imaginary components. There's going to be a phase shift of the photoelectron that goes through all of that electron density of the neighboring atom, and there'll be an amplitude of whether it scatters or not. And then it returns home. So the photoelectron goes out, scatters, and returns home. And so it's e to the I kr, capital R, e over kr, e to the I, capital R over capital R, and then these terms for the scattering of the neighboring atom. And we turn that into, turning that complex number into a real, we take the complex conjugate and so on, and we get a sign function from those exponentials. So we get f of k over kr squared, and then the sine of 2kr plus delta k. And that's the XAFS equation for one scattering atom. And it's just that photoelectron going out and scattering and making it back to the absorbing atom. And it's just the amplitude of that spherical wave going out, scattering, and coming back that is the XAFS. So we could say we're done at this point, but of course we're not done at all. Because that's for one atom. And for n atoms with thermal and static disorder and so on, there's a mean square disorder in R. And we understand at this point that this is not the complete way to describe disorder, but we'll come back to that in later videos. So now we could say there's a coordination number and add a term that gives a distribution of distances. And then a real system has atoms at different distances and maybe different atom types. So there might be oxygen, sulfur, iron, silicon, and so on. So we'll add all these contributions together with a sum over either shells of atom or distances to different specific atoms in the molecule or solid. And we get an equation that looks a lot more like our XAFS equation. This is getting pretty close to what we actually use. Now let's go look at what the scattering amplitudes and phase shifts are. The scattering amplitude, F, and the phase shift depend on the atomic number. I said this earlier, but here are some plots of the calculated values that we use for modeling the XAFS from the program called FEF, which is for this F, effective. F effective is FEF. So you can see here that F extends to high K, but it also depends strongly on the Z, on the atomic number. So for oxygen, it's pretty low out at high K. For iron, it gets higher. For lead, it does this weird thing where there's this sharp drop, but it persists out to higher K. So for heavy elements, there's a structure in F of K, but it also the amplitude is higher, especially at higher K. The phase shift is a little harder to tell what's going on, but one thing I want you to know or see in this picture is that it always drops, and it's got a slope this goes from 0 to about, like, here's minus 15 and here's minus 15. So it drops and has a slope that's about minus 1. In fact, that's often the case. Now, I'll come back to that. Actually, I'll come back to that in later videos, but for now, just try to keep that in mind, or maybe it'll be on a quiz later. And this also has some Z dependence. It's harder to tell in this plot, but there actually is significant Z dependence there. So these complex factors allow the XAFS to distinguish species of neighboring atoms. So you can usually tell the atomic number of the scattering atom within a few, plus or minus 5 or so. See, iron and oxygen can definitely be told apart. Oxygen and sulfur can be told apart, but iron and manganese are not going to be told apart. And this is common for other electron and even X-ray scattering methods, as opposed to some other methods that have strong and discrete scattering factors. Electron scattering and X-ray scattering are pretty continuous with Z. In our XAFS equation, we left a lot of stuff out, as you might imagine. So I'm just going to mention some of these things, not so much to scare you, but to allow you to keep in mind what we also need to include. In fact, I'll go over some of these things here, but there are other things that I'm leaving out. So in the simplest description so far, we're close, but we're not there. So we missed some stuff. We missed what are called inelastic losses. So the electron goes out and it scatters and then it returns back to the photoelectron. But other stuff can happen too. Electrons, that's an electron moving in a solid. So there are lots of other scattering mechanisms that can make that photoelectron scatter away someplace else or lose some energy. And if it loses energy, it's not elastic and it won't overlap exactly with the outgoing photoelectron, so it'll be lost. There are also intrinsic losses as the absorbing atom changes or relaxes that core hole. And then there are also factors that I haven't described yet for multiple scattering of the photoelectron. The photoelectron can go out, scatter once, scatter again, and then come home. The calculations should all include these effects, and they mostly do, and we'll describe them in some detail. The most important one, I think, for understanding XAFS, though, is the mean-free path, or the extrinsic losses. So to get our XAFS equation, we used a spherical wave for the photoelectron. We said it was e to the I kr over kr. But this ignores two things. First, it ignores that the photoelectron can scatter inelastically. That is, it may not be able to get back home to the absorbing atom intact and at the same energy. An electron of 100 eV moving in a solid will have a lot of other electrons that can scatter from. Even slightly losing energy will be a loss of elastic properties. In addition, the hole in the core electron level has a finite lifetime. Eventually, that's going to be filled by fluorescence or the Auger process. So there is a finite lifetime, and that can also limit how far out the photoelectron can go and still make it back home to the same absorbing atom. So the core atom can't change and the photoelectron can't scatter elastically, or if it does, it'll be lost. So a mean-free path, turns out, describes this, how far a photoelectron can go pretty well before it loses energy or coherence with the outgoing photoelectron. So if we can account for this just by changing our spherical wave into, with a term like e to the r over lambda, which adds another term to the XAFS equation, and we get then this term 2r, that's going there and back, over lambda. So that's now our XAFS equation modified for this mean-free path term. And if we plot the mean-free path, we see it looks like this. In fact, this is a nearly universal curve, at the U-shaped curve for lambda. It's mostly independent of system and but it also depends strongly on wave number of the photoelectron. In the normal extended XAFS regime, say 3 to 15 angstrom, lambda is low. It's under 30 angstroms for sure, and it might even be only 5 or 10 angstroms. So that means that the XAFS is a local probe. That, along with the 1 over r squared term, XAFS is a local probe because of lambda. Also for XANES, in this plot, it's a little harder to see. Actually, the Pfeff calculations for lambda aren't perfect for very low energies or wave number. But for XANES, say below k of 2 or so, both the lambda and 1 over r squared term get large again. And so XANES is not really so much a local probe, or at least not as much as extended XAFS. That in the XANES, you can really probe or be sensitive to structures that are 20 angstroms away or so. So the next important term that we haven't discussed yet is the amplitude reduction term, which is due to the relaxation of other electrons in the absorbing atom. That is, we talked about the relaxation due to the core filling, but with an electron ripped out of the core level, ripped out of an iron atom, the other 25 electrons in that atom can relax. And that's what this term is, this amplitude reduction factor, as the overlap of the n-1, the 25 electrons, with the ground state. That relaxation can also give some reduction in the amplitude. Now, this should be calculated reasonably well by the XAFS modeling that we do. And it's usually taken as pretty close to a constant, but mostly we use this as a fitting parameter that multiplies chi. So it's completely correlated with n. It's just a factor that goes out in front. It's independent of k, like the coordination number. And so, but it also masks a lot of other experimental or theoretical challenges, that is getting the normalization of our XAFS spectra or understanding the effect of changing resolution between different beam lines, can also like go into terms that are similar to this. And so using this number of that's about 0.7 to 1 is as a fitting parameter in the XAFS is common and usually necessary to get coordination numbers correct. But it's also slightly unfortunate that the amplitudes are much harder to deal with, to get correctly in absolute terms than the phases. And so this term, along with the normalization challenges of the spectrum, make XAFS amplitudes and so n less precise, more like 10% level than the phases, and therefore the distances. And we'll need to think about S0 squared in almost all the analysis that we actually do. The sum of the XAFS equation, as I mentioned earlier, is the sum of the scattering paths for the photoelectron. And this allows us to take into account multiple scattering, where we have not only single scattering back to the neighboring atom, but also triangular paths or so-called focused multiple scattering paths, or going back and forth multiple times. The formalism that we use treats all of these exactly the same, so that r is really the half path length. So here r would be this distance, the half of the path length for a path, for a scattering path. And so there are lots of paths that we can include. For the most part, single scattering is where you want to start. Multiple scattering might be taken into account. Triangular paths with angles between around 90 degrees are usually not so important. There's not strong scattering, but there are lots of them available in a system, so they might need to be included in the modeling. And linear paths with angles around 180 degrees can be very strong and can be, as the photoelectron sort of gets focused through the center atom here. And those can be that can be useful for determining bond angles. And so XAFS, in that sense, is not simply dependent on R, but is three-dimensional, but is also important to keep in mind when modeling data past the first or second shell. In the first shell, multiple scattering is hardly ever really needed. In the second shell, it's often needed, but not always. Okay. Another complication that I haven't really described much in detail is the synchrotron radiation. So for most XAFS measurements using synchrotron radiation, a synchrotron beam X-ray beam is highly polarized in the horizontal plane. This is generally okay. A photoelectron from a K shell goes out as P, so it's a cosine squared orbital, it looks like this, and it's mostly in the horizontal plane. In fact, for K shell, you're not sensitive to atoms that are directly above or below it in the frame of reference of the experiment. This can be useful for looking at or needs to be kept in mind for looking at anisotropic systems, so surfaces, non-cubic crystals, and so on. This can be important. It can also be useful, or it can be confounding. And anisotropy of the crystal doesn't really matter so much as anisotropy of the local structures. So if a metal atom is all in octahedral coordination, even if it's in long chains, there may not be much polarization dependence. But also, on the other hand, absorbed ion on a surface, or an ion intercalated between a layered material, may show very strong polarization dependence, even though it's an atom, a bare atom on a surface. There can be very strong polarization dependence. So those are important to keep in mind, but it doesn't really change any of the things we talked about so far in the scattering. It's just that there's this additional cosine squared term for K shells. For L absorptions, it can be a little bit more complicated. Finally, I'd like to mention that the XAFS measurements that we do is a snapshot of many, many measurements. So each absorbed X-ray generates one photoelectron. That photoelectron lives for a very short time. The lifetimes are on the order of femtoseconds, but that's much faster than the timescale of any thermal vibrations. So really, every absorption is a snapshot of a frozen structure. But the XAFS measures lots and lots of measurements. So every energy point in an XAFS measurement will be 10 to the 4 to 10 to the 10, or maybe even 10 to the 12 different events. And so we're taking a billion snapshots, but we're averaging over them. And so far, we've put all of this disorder that we would see, whether it's thermal or static disorder, into a single parameter, sigma squared. And more generally, we would want to say the XAFS is a sampling of a pair distribution function, or G of R. That's the probability of where the atom is at a distance R away from the absorber atom. For now, we'll just note that we may need to take this into account. We may need to modify this what I'm calling here sigma squared, or n times sigma squared even. We may need to make that more complicated. But in reality, that doesn't really complicate our interpretation of the XAFS, except for how we model it. But the basic theory is the same for the XAFS. So to recap, with all those complications and caveats, we still have an XAFS equation that's pretty useful. There's a coordination number, distances in the oscillatory term, in the sine term, and then a sigma squared term. And then there's this F and delta, amplitude, and a phase shift in the oscillatory term, and a lambda. And if we know these terms, F, delta, are photoelectron scattering factors for the neighboring atoms, and we know lambda, we can determine our coordination values, proper characteristic values for distance to the neighboring atom, coordination number, and mean square disorder of the neighboring atoms, or some more complicated terms for describing the disorder. And because F and delta depend on the atomic number, we also have some specificity in the neighboring atom type. So in conclusion, we have an XAFS equation that we can use. And in later videos and demos, we'll show you how to use this for analyzing XAFS data. Here's some links for more information on X-rays and X-ray absorption spectroscopy. And if you have any questions or comments or suggestions for how to make this better, leave them in the comment section below, or contact me or ask other people involved with these courses. Thanks.